Hello, bonjour. Welcome to the 10th tutorial of Statistical Mechanics, Algorithms and Computations from the Physics Department of École Normale Supérieure. We have now come to the end of a long journey. And after almost 3 months of travels and of struggles, time has come to revisit the landmark sites that we have seen during the last 2 months and a half. In week 1, our mascot was this pebble. We used it on the Monte Carlo beach and on the heliport of Monaco, as well as in the homogeneous and inhomogeneous 3x3 pebble game. It illustrated such essential concepts as detailed balance, aperiodicity, and irreducibility, as well as the metropolis algorithm. In the homework session, it came up in the 1/2 rule that we used many times since. So, please remember the pebble from week 1.
In week 2, we moved from pebble to disks. This gave us the opportunity to discuss about molecular dynamics and Monte Carlo methods. We were plunged in deep discussion and questions in physics, the equivalence between Newton dynamics and the Boltzmann statistical approach. This is one of the big mysteries in physics, the so-called ergodic hypothesis, that you actually prove to be valid for hard disk in homework 2 using Monte Carlo methods, direct sampling and Markov chain, and molecular dynamics.
During the 3rd week, we went one step further and turned our attention to phase transition, which are one of the main subjects of statistical mechanics. With the help of this object, the clothespins, you have studied the case of one-dimensional hard spheres. And you realized that by conceiving a direct rejection-free algorithm, it was also possible to compute the partition function and to show that the system presents no phase transition. Following the same way, you have also understood the origin of the famous Asakura-Ozawa depletion interaction. In the homework, you turned your attention to the case of the 2-dimensional hard disks, and you understood how this very same interaction was responsible for the existence of phase transition in this system, as famously shown by Alder and Wainwright in 1962.
Week 4 was dedicated to the relation between integration and sampling. We moved from the sampling of points on the surface of a sphere, like this basketball here, to the Maxwell distribution of velocities in a gas and the Boltzmann distribution of energies, and also to essential concepts like discrete sampling and sample transformations. In the homework, you performed integration and sampling in no less than 200 dimensions.
During week 5, we turned your attention to the case of the quantum particles. You learned to deal with their statistics using a tool, the density matrix. You remember this slinky? It embodies the path integral that you could construct using 3 simple properties of the density matrix: the convolution property, the Trotter decomposition, and the solution for the free particle. With those tools in hand, you learned how to construct, using a sampling approach, quantum Monte Carlo algorithm to evaluate numerically the density matrix. During the tutorial, you also learned how to perform the imaginary time rotation and to study the dynamics of one particle in one dimension.
Week 6 was also dedicated to quantum mechanics. We introduced the Levy quantum path, a direct sampling Monte Carlo method for path integral. You use this method in the homework both in its free and harmonic version. In the tutorial, we start to discuss about bosons and Bose-Einstein condensation, which takes place in experimental cells like this one.
Week 7 was all about Bose-Einstein condensation as it takes place in Alberto's experimental cell. It can be looked at and manipulated by lasers, so I hope you all wore your glasses. But seriously, it was about a true quantum phenomenon, the indistinguishability of bosons, and about our glorious 40 lines program, harmonic bosons.py. In the homework, you dealt with bosons and traps shaped like cigars and even pancakes. This sounds like fun, and it was a lot of fun, but it was also a serious, non-trivial quantum mechanics problem.
In week 8, we returned to classical physics and to the Ising model of spins on a lattice with a rudimentary nearest neighbor interaction. From exact enumerations of plus and minus spins using the gray code, we moved on to a discussion of local Monte Carlo methods using the metropolis and the heat bath algorithm, and to the fabulous cluster methods. And do you remember the story of coupling?
During week 9, we went on discussing our beloved models of statistical mechanics. In many of these models, events occur at random times. And during the lecture, you learned how to sample the times between those events without having to wait for them to occur. And in this way, you constructed faster than the clock algorithms. During the tutorial, you were introduced to a basic but very interesting strategy, the simulated annealing, and it allows to deal with complex optimization problems. For instance, you have studied the case of the 13 spheres problem, and you were able to devise an algorithm which finds the best solution to this problem in a few seconds.
So finally, week 10 was the alpha and the omega of Monte Carlo. The alpha was where it all started, in 1777 with Buffon's needles, thrown randomly onto a parquet. And the omega was where it all ended, with the famous Levy stable distributions for observables with infinite variance. So, this was it, statistical mechanics, algorithms, and computations. There were many subjects that we left out, but you will agree there was a lot of stuff inside. So now it is time to present the members of the team who were not in front of the camera during all this time. So let's start with Maxime Berman.
Hi everybody. I had a lot of fun producing the best animations possible for the course, including the histograms, the cascades of configurations, and the pebbles thrown on the Monte Carlo beach.
Then there is Tommaso Comparin.
Ciao! It's me who looked after many of the programs and also typed the subtitles for the course, including the ones you are reading now. I hope this turned out useful for you.
Then there is Émilie Noblet.
So hello everybody, I was the camera woman on this project and entirely shooting the green screen technology.
In addition, there was more camera by Frédéric Borja and our editor, Baptiste Ribreau, who put all these pieces so nicely together. So, thanks to all of you, all over the world, for your interest and your active participation. You made this course happen. And now, let's have a party. Okay. Okay. Bravo, bravo. Et au succès. Ok, so cheers et bravo, bravo. Bravo, bravo. Ok, bravo.
Hello, bonjour, soup brada.
Bon, est-ce qu'on peut peut-être le reprendre? Excuse-moi pour d'autres raisons. Parce que je mettais le truc comme ça.
Welcome to the 9th and final version. Je reprends.
Pourquoi tu le fais?
9th version.
Once you're finished checking all the neighbors of this spin, you take it out of the cluster. Merde! Encore une fois.
Download, run and modify the program Anil
In the homework, and we wish you luck.
Porca vacca.
The cool.
This is something that you should. The program simulated. Ok. Ne passe plus. Dai, sinon on ne termine plus. Hein? C'est vendredi pour tout le monde. Bonjour. Non.
Oui, voilà. Je vais juste marcher une minute là.
Soupe, fais soupe. Ça, on est à l'école soupe.
Soup. Oui, oui.
Je coupe.